My name is Nick Yosha. I run the 3D department here at 3D Print Colorado, and this is Nick Conklin, one of our applications engineers, gold certified Artec 3D scanners. A little bit about us. We have been a Artec partner for about 6 years, I believe now, and we are a gold certified partner, which is the highest level of certification that Artec has, which we've basically been since day one. And we're not the longest standing gold partner in the States. We're one of the longest standing, and there's only a handful of gold partners in the country. You achieve gold certification in a number of ways, or by a number of metrics. One is you have to achieve certain sales status, as well as exceptional product knowledge. And so we are fortunate enough to have a really amazing team here. The scanners that you're seeing here are the handheld line of scanners, which we'll be focusing on mostly today, but we will discuss the others in a little bit here. What we have right here is the Artec Space Fighter. It has an accuracy of about 50 microns and a field of view about the size of a postcard. And we will demonstrate all of these scanners that you see here in just a few moments. The next one in line is the Artec EVA, which has a field of view of about the size of a sheet of paper and an accuracy of about 100 microns. Really good for objects the size of call it a football on up to maybe the size of a car, somewhere in there. There really is no max limitation as far as what they can scan, but that kind of seems to be the sweet spot. The Space Fighter has a sweet spot of about the size of call it a basketball, down to the size of what we'd say a baby's tooth. And then this is the Leo that has an accuracy again of 100 microns, has an adjustable field of view, and great for objects similar in size to what the EVA does, a football on up to even bigger in that case, and can do large objects faster. So we'll kind of jump into the differences of those here momentarily and the scanning process. One thing noteworthy is that the process that you see us doing as we go through this is more or less the same for all three of them. It just demos best to do the Space Fighter, and so that's what we're going to show today. Please, as we go through, we do have this muted and we are recording this, but if you have any questions, we have Davey over here watching the chat to see any questions coming in, and he will be asking if he'll be relaying the questions to us. The other scanners that are in the Artec portfolio that we won't be demonstrating today are the Micro and the Ray. The Micro, as its name kind of applies, is designed for objects that are smaller than 4 inches and has an accuracy of 10 microns. And the Ray is a long-range scanner and has sub-millimeter accuracy and will scan out to about 100 meters. So that kind of rounds out the product family that Artec has. It probably is noteworthy here that you can use the scan data from each and all the scanners in the same environment as well. So if you have a larger object that you want to scan and have an area that you need the extra high resolution from, say, the Space Fighter, you can use those two scans in the same environment and stitch those together. So with that being said, why don't we go ahead and jump into a quick demo. We're going to start with go big to small, I guess, and show the process. Again, once the data is collected into Artec Studio, which is the software where we use the scan data to stitch together and go through any editing functions, that process is the same. So, Nick, why don't you go ahead and do a quick demo of the Leo?
Right, so to explain what you're going to see up on the screen is I've got this thing doing a screen share. So you'll be seeing what I'm seeing on this as I'm scanning. The major differences with the Leo are it's tether-free, it's got onboard computing and a battery, so you don't have any data or power cables running from it, which is very different than the EVA and the Spider, which you'll see momentarily. So you're able to collect data in a much quicker fashion due to the field of view. It also utilizes lasers in its tracking, where the other scanners are purely structured light, in so much as they track and keep positioning via their the changes in the geometry it's scanning, in addition to the texture, the color data. It uses that for positioning as well, which is fairly unique to Artec and enables you to scan without the need to add tracking dots to the environment. So you can see as I scan Nick here, hair does not scan very well, and that's due to the fact that it scatters the grid that's being projected and measured from. So objects that are like clear, translucent, stuff of that nature can be difficult to scan, but we can overcome that using various coatings and methods. We'll get into that more a little bit later. We've actually scanned a mirror with a Leo.
All right, so that is a quick demonstration of how the data is collected using the Leo. Right now, it should be noted, all you're seeing is essentially point cloud data, random points in space, not very useful yet. That's where Artec Studio will come involved to make it files that are workable, depending on the software and what you're trying to do. Nick is actually just plugging in the Artec EVA right now, and we will show that scan process here. In fact, maybe if you'll hand me Cornelius here while Nick's setting that up. All right, so this is Cornelius. We will start the scan process. Cornelius here, can you reach that?
Yep.
All right.
So this time what you'll be seeing is objects populating into Artec Studio, the processing software. This is on a workstation laptop, fairly robust. So instead of just kind of the onboard display of the Leo, we are now actually scanning and utilizing the Studio software.
Are you sharing the screen, or is it still the Leo that's being shared?
No, it's I got both screens shared here.
So functionally, the way all the scanners work is what they're doing is projecting a grid of light on the object and measuring that deformation. The EVA that you're seeing here, as well as the Leo, is projecting a white light, and the Space Spider is projecting a blue light. And so you can see the field of view is considerably smaller in the EVA than it was in the Space Spider. In the Leo rather. Nick, here's a Space Spider for you.
Thank you.
And so it is collecting data at 16 frames per second. The Space Spider coming up will capture data at 8 frames per second, and the Leo is adjustable up to 80 frames per second, depending on the environment that you put it in. And so you can see how much data the Leo captures as it compares to the EVA so far. But again, as we said, the process is the same. The other thing that's noteworthy, if you'll notice, we haven't used any tracking dots whatsoever. That's one of the beauties of the Artec scanners, is that we don't need tracking dots for purposes of scanning. What we use is the geometry and the texture of the object in order to keep tracking. So in Artec nomenclature, texture simply means the color of the object. So, for instance, if we were to scan the carpet might look very repetitive, and there might be very little geometry differences. However, there's enough texture differences there that the scanners scan carpet really well. Same thing with a wood grain table or Lazy Susan or something like that. Nick, are you ready to start the demo here on the Space Spider?
You got it.
All right, great. So I'm going to go ahead and we're going to change this camera view here. There it goes. Just 1 second. All right. So now we have this little toy here. You can see that we are basically going to scan and reverse engineer. We've got this on the Artec little turntable, and the process is going to be the same thing. Go ahead, Nick.
Right, so what you can notice right out of the gate here is my field of view is much smaller, as Nick alluded to earlier. And my standoff distance is much closer to the part. So to give you a visual on the standoff distance, you'll see to the left of the Artec Studio screen, what I'm circling with my mouse here, is a distance histograph of where the scanner is actively collecting data. Right now I'm in a preview mode, which lets me set this up and get everything kind of where I would want to start a scan from. So we're jumping off from a good starting point. But to illustrate, if we get too close here, the object kind of fades from view and nothing's being recorded. Same story goes for too far away. So in your preview, you want to get the proper standoff distance established and have a couple different sides of the object in view. In this case, we're going to use kind of the top of his head here down to his feet. Pretty happy with that. And my histograph. So just one button operation, and now I am recording data. We're just going to slowly spin this turntable and work some angles with my wrist to get a few undercuts and cavitations. They are structured light, so that means, if you can't see it with your eyes, it's not going to be able to take measurements from it. So for an example, if there was a thin cylinder running all the way through this part, it would be able to get the location data as well as the size of the cylinder and see down, a decent amount into it, a couple millimeters depending on the width. However, it will not be able to get the entirety of that cylinder.
You can see the rate at which we're scanning the smaller objects is much, much smaller by design because of what it is we're scanning and the process in going through and the object itself.
So you might have noticed I've moved the object in physical space here, and that's to get the underside, to get the details on his feet, as well as get some undercuts, which were tough to get, such as under his chin here. So we'll go ahead and collect this data set and then one more physical orientation, and we'll show you the process of how to align those data sets to each other as they scan in kind of haphazardly aligned and just floating off in space. The software doesn't know that I physically move this object, so in further processing steps that we're going to demonstrate, I'll show you how to go ahead and piece those back together. It's pretty neat. It leverages some fairly sophisticated feature recognition algorithms, and it uses user inputs to speed those along. So we can drag and drop some points pretty haphazardly. They don't have to be very precise, but you're just giving those algorithms a starting point so that it requires less processing time. So everything we do after the data has been intaken into Artec Studio can be done in an automated autopilot function. You collect the data and you tell the system a little bit about the object you were scanning, and then you hit go and you can walk away and come back to a finished model. We typically like to show the tools hands-on because sometimes they run quicker, in fact, and other times they run so quick we can't even explain what's happening on screen. So as you see, it's just it's very obviously not the alignment we were hoping for. So let me just go ahead and collect the data for this last orientation, and then we'll go through the processing workflow.
Davey, do we have any questions over there so far?
Actually, yes. We've had some people email some questions. Let's start with the first one. How about what file types can you export?
Excellent question. And as we go through this process, we'll actually show the whole stack of file types that you can export in. The most common are going to be your STLs, OBJs, PLYs, basically any type of tessellated or point cloud data. That is what you can scan into or export out of Artec Studio software.
Excellent. We'll ask one more and then we'll keep going. So I use SolidWorks. How do I get the scan data into SolidWorks?
That's actually a really good question too. A lot of people use SolidWorks. SolidWorks doesn't like point cloud and tessellated data very well. And so in those situations, we'll tend to use a third-party piece of software to either do what we would call an auto surface and turn it into a step, or go through a full reverse engineering process and turn the model into a as-built model as if it was built in SolidWorks. We will actually be doing a webinar 3 weeks from today, I think. I don't know if we've sent any information out on that yet. So if you haven't seen anything, we'll actually be doing sending out some emails on that shortly. I believe it's 3 weeks from today about scanning into SolidWorks as well. So mark your calendars. Can't miss it.
Leonard says DesignWorks works great.
DesignWorks is also another good one. That's right.
Alrighty. So what we're looking at here are our 3 data sets, and we're going to go ahead and isolate out the turntable that I scanned these on. That's not necessary to our processing. So I'm going to use a cutoff plane, which is a favorite of mine, and we just take a quick paint sampling of the base, and it puts a best fit plane through it, and you can adjust it up or down if it doesn't get it perfect. And just like that, the noise is isolated out, and we're ready to combine these. There are other editing tools that are quite good if you aren't able to use a plane and need to get more three-dimensional erasing abilities. You can use a lasso tool here, which I actually got a little too much of my part there, so I'm going to go ahead and deselect. It should be noted that we don't need to delete out all this noise at this stage of the process. That would just waste too much time. There's ways to deal with those in automated fashions. So now that we've gotten rid of the base, we're going to go ahead and jump into our alignment stage. Cool. So in your alignment stage, it picks the top scan by default to be your keystone scan. And what that means is that is the scan that every other scan is being connected to. That's not always the best option to use, so you can just double click and it unselects it, and now you can choose another group for your keystone scan. In this case, I will stick with this top level one. What you're looking for is just good data on all sides, so it becomes easy to drag and drop points and get everything aligned. So with just those 2 points, it's going to dial these 2 scan groups together. And I'll go ahead and I'll run this one with an automatic alignment so you can watch the time savings just drawing those 2 points on his eyeballs made. It was near instantaneous when I ran it with the 2 points that I inputted, and as you can see, using the automated methodologies, it's taking a little longer processing time. But in the end, the result is the same, and we're ready to proceed. So one thing I really like about Artec Studio is the user interface is super intuitive, and it does a good job of balancing ease of use for a new user, as well as giving you easy access to sophisticated functionality should you be a power user. So some of the things I like is everything's laid out from top to bottom in the order you'll be using the tools. And when you go into a menu, you can get these drop downs, and if you're kind of a new user or a novice, you can just use it as is and process them through top to bottom. Or if you start to get in depth with scanning and learn your tools a little more, you can use the drop downs here and have finer control over how the algorithms process through this particular data set. And something worth noting is you don't have to memorize any settings. So by default, it keeps our feature search radius here at 5. If I go and type 78 there, this would be processing probably till lunchtime. So we don't want to do that, but you'll notice that it filled this checkbox in. So if I go ahead and click that, it restores it to the manufacturer's recommended settings for the particular scanner being used. Nick mentioned earlier that you can use each and every scanner in Artec's product line in the same environment, in the same project, And we've done that quite a bit. We use this example day in and day out of Rhino racks. We'll go and we'll either use the Leo or the Eva to scan the roof rack area of a car's roof, and we'll kind of get a skeleton with the Eva or the Leo, and then we'll go in with the Spider to get the mounting locations with higher fidelity.
So we have another question that came in from Larry. Does the mouse rotation work like SolidWorks?
That's a very good question. You have control over it, so if you're comfortable with how SolidWorks navigates three-dimensional space, you can change your settings to have the same shortcuts. Another pro tip would be to double-click in space, and that sets this purple pivot point. So if you ever find your object's not moving according to how you think it should be, just go ahead and double-click, and now that'll be your new pivot point. So you do have control over your keyboard commands and your mouse commands to manipulate 3D space. So while I was answering that question, I ran an algorithm known as global registration in the background. And global registration goes through and starts to look at the scans as a whole entity instead of separate groupings. And it also goes ahead and assigns a max error, which is a unitless metric that Artec uses to tell you how well your scans are piecing together. So for example, in this first group, I have 381 frames, second is 450, third is 300, and I'm seeing a max error of 0.3. So the higher the max error, the less accuracy and resolution your end model is going to have. So what I can do is I can control this a little bit. You see I've selected, call it 7 or 8 different frames out of that 300 plus that have this 0.3 rating. I'm going to go ahead and just delete them, and that'll make it so my new highest max error is a 0.2. I'm going to go through and do the same thing for the other scan groups here. This one only had 2. Perfect. So once you get a max error that works for your accuracy needs, you can go through and choose a fusion algorithm. I'm going to go ahead and start one in the background here and then kind of explain what I'm doing. Should be noted that I'm running the algorithm at 0.3, which is 0.1 higher than my highest max error. And that is what Artec recommends, to always go to 0.1 higher than your max error. So if I had left those 0.3s in, I would have had to run this at a 0.4. So I chose a sharp fusion, and that's kind of a happy medium between fast and smooth fusion, the other two options. So to walk you through them, we have fast fusion, which, as the name implies, it's going to give you a result in the least amount of time. It's the least computationally heavy fusion algorithm. It's also actually going to be your most accurate option. It doesn't patch or repair holes in any sort of fashion. What you scan is what you get. It's really, really good for comparison and measurement purposes. Maybe not the best for applications like 3D printing. So smooth fusion is now a polar opposite from fast fusion. It's going to be a single core operation, so it's going to require the most amount of processing time. It's also going to go through and distort your data the most. It's going to smooth surfaces and try to give you a nice, consistent finish. Really, really applicable in the art world and taking stuff to 3D printing. It also has intelligent hole filling abilities. So it'll sample geometry around a section which doesn't have data and attempt to put a best guess as to what should be there. That's also available in the sharp fusion, which is what I ran for this. So sharp fusion is kind of your happy medium. It's going to be faster than smooth, but not quite as fast as the fast fusion. And it's going to give you the ability to patch and repair holes. So we just got a result here. Looking pretty good. I always like to run a small object filter, which is just a way to isolate out some of that noise I was referencing earlier, which wouldn't have made sense to go through and erase manually. So this right now is exportable to any kind of mesh family format, and I'll show you what we have. So STL's the most common by a long shot. We also have polygon files that have texture data as well. So your WRLs, your PLYs, OBJs, et cetera, et cetera. So from here, we can go ahead and we can edit this model with the same tools that I was using to edit the raw scan data. So I can take my eraser tools, get rid of sections, I can smooth sections out. In fact, I'll go ahead and do a global smoothing here just to show you that. And goes through and kind of smooths out the surface globally. You can apply that with a paintbrush if you wanted to reduce a certain area, maybe down here in his neck where it bridged a little data from the hole filling. And just like that, we're working on a section and not globally. There's also defeature brushes, there's some hole filling and patching repair tools. I'll actually show you that right in this area. You can see it bridged where his little weapon meets his leg here. You can see on the webcam that, there we go, it actually does not touch there. So in order to fix that, what I would recommend doing is jumping into our erase tool and using a 3D selection. I'm just going to go ahead and break the chain between the leg and his weapon here. Once that's broken, I'm going to go into my Fix Holes tool, and I'm going to actually add a bridge. If I was to attempt to fix these two holes without doing any other aspects to this, it would attempt to bridge them again, and we don't want that. So we're going to help the software figure out that those are two separate entities. We're going to do that by building a bridge.
Nick, while you're going through and doing that, David, it looks like we might have received another, excuse me, another question.
Yes, sir. So Ralph asks, what kind of light shines on the turntable?
Right, so it's projecting a grid onto the object, and the grid for the spider in particular is too small for the human eye to pick up. We can somewhat visualize it in person with the EVA. However, it doesn't translate via webcam very nicely, so you're just going to have to take our word for it. But it's wrapping a grid around this object, and it's being projected onto it, and then it's measuring how it deforms around the various features, and that's how it's calculating geometry. There's also texture flash, which you might be witnessing through the webcam, and that's so it can capture the photorealistic color data, and we'll show you that in a moment here.
So in the scan data, we can show you it's generally capturing texture data every 6 to 15 frames, something like that, depending on the scanner and the settings that you have there. Beyond that, and all the light sources that you're seeing were coming from the scanner itself, nothing externally other than standard normal light. If you are scanning for something in a photorealistic application, if you're having products on the website that you want to sell as opposed to using a bunch of photos, and you want to have an object that is, you can spin in real time, zoom in, zoom out, have measurements, potentially allow somebody to use a phone or goggles or tablet of some sort to see, say, a couch or something like that in their real environment, to make sure that before somebody goes and drops $5,000, whatever it might be, on an expensive couch and see what it looks like in your place. This type of technology will allow you to see exactly what it's going to look like before you actually bring it in and have it in there. So the lights that we scan in, we really only change if we'll only put something in like a light box or something like that if a true photorealistic scenario, as if you're doing true photos for websites or anything like that. The better light, the better it's going to look in a photorealistic model.
And something worth mentioning is the grid that it's projecting onto the object, at least for the Spider and the EVA, can quite easily become overpowered if you're scanning in an outdoor environment on a really, really sunny day. The sun can overpower that grid, so it's no longer able to calculate the geometry. So for those situations, we recommend like a tent, tarp, and to be honest, it has to be fairly sunny for that to become a factor. You can get away with scanning in overcast conditions. It's not as big of an issue with the Leo, with the laser tracking capabilities. However, at that point, in a direct sunny condition, you'll be capturing geometry, and the texture data might be a little washed out.
All right, Nick, did you already show the file types that we can export out right now?
I did, yes. I
Okay,
can
great.
bring those up again.
So right now, this model is exportable to any standard CAD package, could go straight to a 3D printer, what have you at that point, dropped into an AR, VR application.
It's hard to see if you could read them out.
Oh, yes.
Oh,
So we have our standard polygon file, PLY. Those can carry texture data if it's been mapped onto the object. We have STL files, WRL version 1 and version 2, OBJ, point cloud data, American Academy of Orthosis, so a couple industry-specific ones. We even have a Walt Disney PTEX file. It should be noted that directly out of Artec Studio, we cannot get any of our solid body formats that SolidWorks prefers to see. So your steps, your IGESs, you are not able to export, and that is where the bridge software that Nick was alluding to earlier comes into play.
and again, we'll be having a webinar on that here in just about 3 weeks. But that basically wraps up today's version of our scan demos. Just going through to see if there's any other quick questions. Do you have any more questions that you've seen here, Dave?
Yeah, we sure do. And I will be emailing some of the specifics to the questions as well. So one question that came in is what is the lead time for scanners at the moment?
That's a good question. So I guess at this point it's noteworthy that we both sell the scanners as well as do scan services. So if either or both of those made sense for you, which sometimes both can make sense, we can help with all of that as well. The lead time to purchase scanners using the EVA and the Space Spider basically can ship within just a day or two, and the Leo is starting to get caught up here a bit. An order today on a Leo will be about 6 months. Apologize for the noise in the background. Apparently they just decided to snowplow our parking lot.
All right, next question. Can you scan clear objects?
Clear objects tend to be a little bit more difficult because the structured light has trouble seeing it. Something like a water bottle or something like that would be difficult. However, we have some ways around that, depending on the object, the end-use goal, and the results you're looking for. We have a couple of different objects here. If it's for an AR, VR type application, and you are going to be adding texture to your model, the Stoling spray works really well. We've done some, I don't remember what brand of hand tools they were, but they were really, really shiny out of the package, and we just used the Stoling spray to knock down the shine on it because it wasn't clear and see-through. That worked really well. That can be picked up at any art shop or anything like that. We can help provide that for you if you need to. The other end of the spectrum would be, this would be the most expensive, that we tend to use a lot for jewelry and objects that have a lot of nooks and crannies in it, where it would be tough to get something like your cheapest object or your cheapest spray. This powder just ends up after a period of time dissolving and goes away, and so you don't have to worry about the cleanup and whatnot. This is fairly pricey. This is $1.99 at any corner shop or anything like that. And so we tend to use a combination of any of those types of things. And if you're doing large objects that have surfaces that repeat, if you're doing the side of a vehicle that has not a lot of texture or geometry change to that, sometimes but it can see and scan in real well for purposes of tracking. Our third object, or our third, whatever you want to call it, will be just some painter's tape that we'll throw into the scene just to make the scanners see the repetition being broken up a little bit more. And are there any other questions here? Let's see, would
you apply baby powder on the model?
Sure, baby powder is another one that works just as well. We have always tend to use one of those, but baby powder would tend to work as well. Baby powder can be a little bit more difficult to apply and can add some clumping to it sometimes. It doesn't tend to spray just as nice, but the concept would work just the same. Is there anything else that we have, Dave?
No more questions at the moment. Feel free to type in your questions as you have them.
One thing I guess I'll make mention here as well. We are very, very happy to provide benchmarks, do a demo specifically to any of your parts. If you want to see how it works specific to your application, any downstream applications, or anything like that, we can take that conversation offline here. You should have my contact information from the emails we sent out, and we'll send this recording out as well. But very, very happy to do benchmarks of your own item as well, and those would be at no charge also. So please feel free to reach out if you have any other questions. That would be great.